friends, this is Priyanka. Today we are going to understand theoretical part as well as numerical part for the reaction turbine with draft tube. I have made 3 parts for this video. In the first part, we will understand the output of reaction turbine when tailoress is above the turbine. In the second part, we will find out the output of reaction turbine with draft tube. And in third part, we will solve numerical and we will calculate the turbine height above tailoress level. Now we will move for the first part. So we will understand output of reaction turbine when tailoress is above the turbine with the help of diagram. When the tailoress level is above the turbine, then this turbine is known as submerged turbine. Now we will understand the different points. This level is known as the headrest level. We will consider the particular point on this headrest level, that is the point A. So above this level there is the atmosphere. So what is the pressure at point A? That is the atmospheric pressure and notation is P to the base A. Now next is tailrest level. So tailrest level is below the headrest level, and at this tailrest level we will consider one particular point D. What is the pressure at point D? Because above the tailrest level there is the atmosphere, and therefore the pressure at point D is nothing but atmospheric pressure PA. Now we will move for the turbine. So this turbine is the submerged turbine. So we will consider 2 points, that is at inlet of the turbine and at the outlet of turbine. So these points are along the same line, that is the XY line. So I have shown here the XY line with the help of dash. So this is the point B, which is at the inlet of turbine, and point C is at the outlet of turbine. Now how we can define the energy at point B as well as energy at point C? So if we observe the working, here at the headrest level there is the water which is in static condition, and while it is passing through the turbine, and because of this extra pressure that is getting generated because of this level difference, there is the difference of level, that is the headrest level and tailrest level. So here extra pressure is there, and this pressure is getting converted into kinetic energy. So while we are writing the energy at point B as well as energy at point C, then we have to write here pressure head at point B, and because the fluid is in the static condition, there is no any kinetic head. And how we can define the energy at point C? There is the pressure because of this atmospheric pressure, and this turbine is submerged below this tailrest level, and that's why pressure is getting generated because of this height small h only. So we have to write this, plus we have to write the kinetic head because the water is getting converted into the dynamic condition, that is from static condition to dynamic condition when it is passing through the turbine, and that's why at point C we have to write the kinetic head. Now we will move to write the energies. So if we observe, energies at all the points are measured taking XY as a reference line. So energies at all the points means what? Energy at the inlet of turbine and energy at the outlet of turbine. So here is the point B and here is the point C. So how I can write the energy at point B? So pressure at point B is there, so I will write PB. So pressure head, how we can write here? So pressure head, we know that P by rho G. How we can write the kinetic head? That is V square by 2G. Now here there is no any kinetic head at point B, so only pressure head is there. So I will write here in rough, that is PB by rho G. But now if we observe this diagram, how we can define this PB by rho G? That is the pressure at point B, that is PB. So I will write here P to the base B divided by rho G. So rho G means what? Rho is the density of water, and if we multiply with G, then it will become weight density. So we will write here PB by rho G. If we observe this diagram, how we can define this pressure head? Here is the pressure PA, that is the atmospheric pressure, and below that there is the height. So what is the height of this headrest level with this XY line? So this total height is nothing but HO. So we have to show this notation H to the base O. So I will write here this HO plus, now if I write this height, then I have to take the pressure, that is the atmospheric pressure, plus PA by rho G. So I will write this PA by rho G plus HO. Now in the same way we will move for the energy at point C. So if we observe here, fluid is in the dynamic condition, so we have to write the kinetic head, that is Vc square by 2g. Now V to the base C we have to take because the velocity at point C we have to consider, plus pressure head. So pressure at point C, that is nothing but PC, and how we can write the pressure head, that is PC by rho G. So if I take here PC by rho G, then how we can write in different way, that is in terms of atmospheric pressure A. Now this point C, if we observe here, it is below the tail race level, and above this tail race level here is the atmospheric pressure. So we can add here PA by rho G, that is this pressure head, plus this height H, because the tail race level to the line XY, the height is H. So we will write here as a PA by rho G plus small h. And we have to also add the kinetic head. So I will write here PA by rho G plus H plus kinetic head, that is Vc square by 2g. So these are the energies at this point B and point C. Now what is the important thing? That is the output of reaction turbine. So how to find out? So for that we will consider W1, that is we will calculate what is the work done per kilogram of water when it is passing through the turbine. So when the water is passing through the turbine, water is in static condition at point B, at point C it is converted into the dynamic condition and kinetic head is getting generated. And here, and why this is happened? Because of this level difference in between head race and tail race. Now how to find out the work done per kilogram of water? So for that we have to take the difference in between energies at point B and at point C. So we will write here EB minus EC. So EB minus EC. So we will take the difference in between these two, PA by rho G plus HO minus, now we have to take bracket, PA by rho G plus H plus Vc square by 2g. Now if we simplify this, here all the terms become minus, that is minus PA by rho G minus H minus Vc square by 2g. So this PA by rho G and this minus PA by rho G is getting cancelled. So I will write directly HO minus H minus Vc square by 2g. Now if we observe the diagram, again we will simplify this. So HO is the distance in between headrest level to this XY line, and small h is the distance in between this tailrest level and XY line. So if we take the difference, that is HO minus H, then here is the distance, that is headrest level and tailrest level. This height is known as the net head, that is capital H. So I will write here capital H minus Vc square by 2g. So this is nothing but the work done per kilogram of water, and notation we have used, that is W1. Now we will move to the second part, that is the output of reaction turbine when the turbine is connected to the draft tube. Now we will understand this diagram. So here is the headrest level and this is the tailrest level, and in between this headrest level and tailrest level, the turbine, location of turbine is there, which is attached to the draft tube. Now if we observe this draft tube is not open to atmosphere. If we observe, the end point or outlet of the draft tube is below the tailrest level. how to find out the pressure at point A. So this point A is on the terrace level, and above this terrace level there is the atmosphere. So we can say that the pressure at point A is the atmospheric pressure PA. Now in the same way we will select one particular point on the terrace level, that is the point E, and in the same way above this terrace level there is the atmosphere. So pressure at point E is the atmospheric pressure PA. We will consider one particular horizontal line, that is the XY, and we will consider all the energy points along the line XY. So here at the inlet of turbine, that is the point B, lies on the XY line, and at the outlet of turbine, that is the point C, which is also lie on this XY line. So we have to find out the energies at point B as well as point C. And at the outlet of the draft tube there is the point D that we have to select. Now if we observe the vertical distance, so what is the distance in between headrace level and tailrace level? That is the net head, capital H. What is the vertical distance in between headrace level and this XY line? That is HO. The vertical distance between this tailrace level and this XY line is small h. And outlet of the draft tube is below the tailrace level. So vertical distance in between this tailrace level and the point D, that is the outlet of turbine, is HD. That is small h and to the base D. So these are the distance. Now we have to define the energies at point B, that is inlet of turbine, then at point C, that is the outlet of turbine, and at point D, that is the outlet of draft tube. So remember, this outlet of draft tube is not open to atmosphere. So when we consider the energy at point B, then it is having the effect, that is the pressure because of this headrace level, as well as on the other side also this draft tube is not open to atmosphere. So we have to consider also the pressure at this point D. So how to write the energy at point B? So we know that below this headrace level water is in the static condition, that is it is not moving. So how we can define the pressure, that is PB, or we can say pressure at point B, that is nothing but PB, and what is the pressure at, that is PB by rho G. But if we observe above this headrace line there is the atmospheric pressure. So how we can define this pressure head, that is PB by rho G. So I will write in the other form, that is PB by rho G is nothing but this PA by rho G, plus we have to add this net head, capital H, plus because the other side is not open to atmosphere, so we have to consider this vertical distance in between this tailrace and outlet of draft tube, that is HD. So I will write here energy at point B is nothing but PA by rho G plus capital H plus HD. Now we will move for the next point, that is the energy at point C. So here this static water is in the static is getting converted into the dynamic condition when it is passing through the turbine or at the outlet of turbine. So we have to write here the kinetic head. So kinetic head, that is nothing but V square by 2G. So at point C we will write Vc square by 2G. So how we can write this energy at point C? So we have to write first the pressure head, that is the Pc by rho G, plus kinetic head, that is Vc square by 2G. Now this point C is not open to atmosphere, but here the outlet is below this tailrace level. So we have to consider this height also. So from this point C to this point D, what is the height? H plus HD, that is small h plus HD. Now we will move to the next point, that is the energy at point D. So how we can define this? So here also water is in the dynamic condition. So kinetic head is also there. So what is the kinetic head at point D? That is Vd square by 2G. Plus pressure head, that is Pd by 2G. Pd by rho g. When water is passing through the draft tube, there is the friction and other losses, and there is the head lost by water. So we will consider here HF, that is small h to the base f is the head lost by water when it is passing through the draft tube. So how we can define the relation in between energy at point C and energy at point D. So water is entering at point C in the draft tube, and here is the outlet at point D, and here in between this point C and D there is the head loss due to friction. So we can say that energy at point C, that is EC, is equal to ED plus HF. So we will use this relation later. Now we will consider W2. So what is this W2? That is the work done per kilogram of water when it is passing through the turbine. So how to find out the work done per kilogram of water when it is passing through the turbine? So here is the turbine and these 2 points, that is the point B and point C. So we have to take the energy difference in between these 2 points, and then only we will get the work done. So we will write here EB minus EC. So which is W2, that is nothing but which is equal to EB minus EC. Now we will write these values, that is EB, we will put this value, and about EC, but we have relation, that is EC is equal to ED plus HF. Now if we observe this whole structure, then this point C is not open to atmosphere, or this is not the outlet, but the outlet is at point D. So we have to write the energy at point C should be in terms of energy at point D, and here is the relation in between C and D, that is EC is equal to ED plus HF. So I will write this, which is equal to EB minus ED plus HF. We will put here the bracket. Now we will put all the values. So what is the value of EB? So here, which is equal to PA by rho G plus capital H plus HD minus, now what is this ED? So ED is here, that is VD square by 2G plus PD by rho G plus HF, and we have to put bracket. Now if we observe this pressure head, that is PD by rho G, we will define in terms of atmospheric pressure. So if we observe this diagram, how we can define this pressure head at this point D, that is PA by rho G plus this height HD, vertical height HD. So we can write PD by rho G, that is nothing but PA by rho G plus HD. So I will write here, which is equal to PA by rho G plus H plus HD. Now at the same time I will simplify this. So all the signs, that is the plus sign, it will become the minus. So I will remove this bracket, minus VD square by 2G minus, now instead of PD by rho G I will write PA by rho G. PA by rho G plus HD. So this plus HD will also become minus HD minus HF. Now again we will simplify this. So this PA by rho G is getting cancelled. This HD is also getting cancelled. So what is remaining, I will write here H minus VD square by 2G minus HF. So here is the final value, that is the work done per kilogram of water when it is passing through the turbine. Now we will find out what is the extra work done due to draft tube. So when draft tube is not attached to the turbine, then work done W1 is getting calculated, and W1 is H minus Vc square by 2G. So what is the extra work done? So for that we have to take the difference in between these two. So W2 minus W1. So if we give here W2 minus W1, so here it will become minus sign, and this minus Vc square by 2G will become plus. So this plus H and minus H is getting cancelled, and it will become plus Vc square by 2G minus Vd square by 2G minus HF. So this 2G is common. So I will write Vc square minus Vd square divided by 2G minus HF. So this is the formula to calculate the extra work done when draft tube is getting connected to the turbine. Now we will move for the third part. That is, we will solve the problem to find out the vertical height in between this turbine and the tail race level. Suppose the value of h, that is it is indicated by the letter small h. Suppose this value of h is positive, that means this turbine is placed above the tail race level, and suppose this value of h is negative, that means this turbine is placed below the tail race level. Now first I will read what is the given question. Find the position of Kaplan turbine with respect to tail race level from the following data if there is no cavitation in the runner. Atmospheric pressure 750 mm of Hg, vacuum at the exit of runner 400 mm of Hg, velocity of water leaving the runner 13 meter per second, friction loss and exit velocity of water head 1.5 meter of water head. Show the arrangement of turbine setting. So this was the given question. Let us first understand the given data. Here atmospheric pressure 750 mm of Hg is given. So we will use here the notation for atmospheric pressure, that is P to the base A. Then the vacuum at exit of runner. Now if we observe this diagram, where is the exit of runner? That is the point C. So vacuum at exit of runner is given. So here vacuum is given. So this is, we will say that the pressure at point C, PC is 400 mm of Hg. But here we have to give the minus sign because this is the vacuum. So we will say that PC is equal to minus 400 mm of Hg. So here I will write only minus 400. Then the velocity of water leaving the runner. So when the water is leaving, that means if we observe this diagram, velocity of water leaving the runner, that is Vc is given. So leaving the runner, that means Vc is equal to 13 meter per second. And friction loss and exit velocity. So here friction loss is taking place when the water is moving from this point C, that is at the entrance of the draft tube, to the exit of the draft tube, that is from point C to point D, and these losses are known as the head losses. So we can say that this HF. And exit velocity. So what is the exit velocity? So if we observe here exit velocity, that is at point D there is the exit. So velocity at point D is nothing but Vd square. So HF plus Vd square by 2g, it is given 1.5 meter. Now we have to find out what is the height or location of the turbine from the tail race. So if we observe, this distance is shown with the letter h, that we have to find out. So we will show here the relation, that is EC, energy at point C, is equal to ED plus HF, that is ED plus this loss due to friction of water, ED plus HF. So suppose we show this relation, and if we put the value of EC as well as ED as given in the formula, that in the previous video we have seen this. So this energy at the different point is the important, so we have to put the values, and when we simplify this, then we will get H is equal to PA minus PD by rho g minus Vc square by 2g plus Vd square by 2g plus HF. So this formula we get. Now we will put the values as the values given from the question. If we observe here, PA is given and PC is given, but in the formula pressure at point D, that we have to find out. So how to find out? So PA is 750 is given and this PD is given, that is PC is given 400. Now if we observe the diagram, here pressure at point C is given, but how to find out the pressure at point D? Now this pressure at point D, if we have to calculate, then we have to take the atmospheric pressure plus pressure at point C. But at point C there is the vacuum, so we have to take the minus sign. And what is the atmospheric pressure? That is, it is given 750. So pressure at point D, PD is equal to 750 minus 400, and which is equal to 350 mm of Hg. So we have to use the same unit mm of Hg. So directly I will use here 350. So H is equal to, now I will put the value Pa, that is 750, minus PD, that is 350, divided by rho g. So rho is the density of water, that is 1000 into 9.81. Now remember, this is having, pressure difference is having unit of millimeter of Hg, but we will convert it into atmospheric pressure. So 1 atmospheric pressure is equal to 760 millimeter of Hg. So we will divide here with 760, and we will also convert this atmospheric pressure into bar, that is 1.03. We will multiply here 1.03 into 10 raised to 5. Now we will move for the next. So minus Vc square by 2g. So minus Vc square is here, that is 13 square by 2g, that is 2 into 9.81, plus Vd square by 2g plus hf. Now here exit velocity, or we can say exit velocity head is given. Now why we have taken Vd square by 2g? Because if we observe, friction loss and exit velocity is given in meter. Now when it is given in meter, that means when unit is meter, that means it is head, and that's why Vd square by 2g is the kinetic head. Exit velocity, that means here head word is not used in the question, but whenever it is mentioned, it is given in meter. So we have to consider here head, that is Vd square by 2g. So here is also head loss due to friction, this is also head, and this kinetic head total addition is given 1.5 meter. So this 1.5 meter we can directly use. When we calculate this, we will get 5.55 minus 8.62 plus 1.5, that is equal to minus 1.77 meter. That is the height in between this turbine and terrace level is minus, having minus sign. That means this turbine is in the downward direction for this terrace level. So we have to show with the help of diagram. So here is the headrace level that we have to show, and this is the vertical distance in between this headrace level and tailrace level. Now below this we have to show the turbine. So here is the turbine. Now I will show here the inlet point B, outlet point C, and here is the outlet of the draft tube, that is point D. So here is the point B, C, and here is the draft tube that is getting connected. Now here along this XY line we have to take all the reference points, and we have to measure the distance h from this tailrace level to this XY line, and this vertical distance is nothing but 1.77 meter.